So what do we start off with? Those first couple lectures are about some generalities. Most important of those generalities emphasize how differential equations are continuous dynamical systems and difference equations are discrete. Differential equations are continuous. I said dynamical systems, basically systems that change over time is what that means. I'll go ahead and use that phrase, dynamical systems. T is the independent variable, where T is a real number. And okay, this is unfortunately difference equations has the same abbreviation. Okay, so this is differential equations. And difference equations, that's discrete dynamical systems. Where the independent variable is a whole number, 0, 1, 2, 3, 4, 5, 6, etc. Sometimes called a non-negative integer. Why do we talk about both in this course? I mean, the course is called Differential Equations and Linear Algebra. It's not called Differential Equations and Difference Equations. It's not called Dynamical Systems, though you could call it that, I think. The reason is because these two things are tied together. And in the linear algebra part of this course, there are very natural ways of talking about difference equations and tying them to differential equations. The most basic examples of differential equations, and that's the word differential if you can't quite tell, differential equations and difference equations are fortunately the simplest. I mean, the very simplest for differential equations is dy dt equals some function of t. And that does come up in the simplest example of free fall with no air resistance. But I want to focus on, more importantly, when the right-hand side is dependent on y, an autonomous equation. The most important here is dy dt equals some constant, I'm going to call it little a times y. Sometimes I've called it little k. Little a times y. That's as simple of a linear differential equation in y that you can write down. Its general solution can be found by separation of variables, but I do want you to just know it. You're looking for a function whose derivative with respect to t is always a times the function, and know that way of thinking about the differential equation. I'm looking for a function of time where t is a real number, where that function's derivative, the rate of change with respect to time, is always a constant a times the function itself. Y is the function itself. General solution is y equals c times e to the at power, where c is an arbitrary constant. Arbitrary constant. A is a specific constant. It's got to match that A. If that A is 5, that A's got to be 5. But C can be anything. Any function like this solves the differential equation. You should certainly be able to check that. It's pretty easy. Moreover, any solution of the differential equation should be able to be put in that form. That's harder to prove. If you add a generic initial condition, y of 0 equals y sub 0, where y sub 0 or y naught is a specific number, a specific constant, not an arbitrary constant, you can solve for c. C has to equal y sub 0. We've seen that, right? Use that initial condition and get your unique solution of the IVP. Y equals, okay, you should feel okay with phi of t notation as well. function name is phi here. That's not, you don't find that in the differential equations book, but I do use that sometimes in the lectures. You should start working at feeling comfortable with that. Y0 e to the AT. Sometimes I even put a subscript of Y0 there to emphasize the initial value is Y0. This general solution represents infinitely many answers. This unique solution of the IVP represents one function, because A is a fixed number and Y0 is a fixed number. I'm not saying what they are, I'm just imagining them to be fixed. What's the related difference equation? The related difference equation is yn equals a times yn minus 1. Or if you prefer, y sub n plus 1 equals a times yn. Whereas you solve a differential equation by separating variables, or in this case, guessing, educated guessing, you can't integrate that. N is a whole number, 0, 1, 2, 3. Well, I guess if I got an n minus 1 there, it would start at 1, though the first subscript could be 0, my initial condition. Initial condition will be y0. Y0 equals itself. Y0 equals y0. It's just some number. I could think of this as an initial value problem as a difference equation. What's the unique solution of that IVP? It does not involve E, or at least that's not the simplest way to write it. What's a formula for y sub n here? That will equal y sub 0 when n is 0. Anybody remember? Taylor series, is that what you said? You maybe could use a Taylor series to help you, but you don't need to. Yeah. A to the, n power. Y0 times a to the n power. Why? Why does that work? Well, certainly when n is 0, a to the 0 is 1. Y0 times 1 is y0. It's got the right initial condition. Does it satisfy the difference equation? Does yn equal a times yn minus 1, no matter what n is? Yeah. Use the property of exponents to write that. Bring this a to the first out as an a in front. And then this thing is y sub n minus 1. If y sub n is this, then this is y sub n minus 1, because I'm just replacing n with n minus 1. It's a little weird, a little confusing perhaps, but at its heart, when you get it, it's very easy actually. No integration necessary. If you didn't know what to guess, how would you solve it? If you didn't know what to guess. I mean, one of you knew what to guess. Don't integrate, instead, iterate. Use this equation over and over again. Yn equals a times yn minus 1. But yn minus 1 equals a times yn minus 2. Y sub n minus 2 equals a times y sub n minus 3. Y sub n minus 3 equals a times y sub n minus 4. What's n? I don't know. But we see a pattern here. That pattern evidently continues. In the end, we want a y0 there, so I'd have to have y sub n minus n. And the pattern is whatever I subtract has to be the exponent there. This is the same as a to the n times y sub n minus n, which is the same as y sub 0 times a to the n. Same thing that I wrote there. You don't need to integrate. With difference equations, you should not integrate. You should use the recursive equation, the difference equation, over and over again. Look for patterns. That does get complicated. Sometimes you did have that one homework problem where you had to use a geometric series, the cooling coffee. Would I put a problem like that hard on the test? Not on the in-class, maybe the take-home. By the way, in the old exams on Moodle and the video I made last year, not guaranteeing all your problems are going to be like those, but I'm sure a lot of them will be similar. This is the heart of the first couple lectures. In the simplest examples, of course, I talk about bigger ideas like pendulum and stuff and phase plane, but those are more difficult kinds of abstract things. This is the most important concrete things. Does this come up in the textbook? Well, this part does in section 1.1. Not in the exact same way that I've done it here, because there's no phi of t, for example, and I don't talk about, and the textbook doesn't talk about generic initial conditions, but they talk about exponential growth and decay models. That's what these are. Coming back to focusing on what the textbook emphasizes, and then I did emphasize in the lectures. In the next section, we talk about separation of variables. Separation, I can't spell. Separation of variables. You did an example, the implicit solution for the class participation today, separation of variables for differential equations. I don't know if you noticed, but essentially all separation of variables are those differential equations where the right-hand side function in general depends on t and y and can be written as a product, say g of t times h of y. You need a product on the right-hand side to be able to separate variables. And in this abstract situation, you would separate variables by dividing both sides by h of y, and again, pretending to multiply both sides by dt. This would be equivalent to saying dy over h of y equals g of t dt, and then you'd integrate both sides and go from there. Ultimately, hoping you can solve for y as a function of t, as you often can. In fact, you always can in section 1.2. We could not in the class participation today, so we needed just an implicit solution. We did the integral and then we stopped. Well, I guess we used the initial condition as well. Actually, you could get stuck here too, right? These integrals could be really hard, if not impossible to do. So it's possible you could have a problem where you could separate variables and get to the integrals. Then you just, I don't know what to do. I don't know how to do these integrals. Have Mathematica try them. So there's just some integrals that you can't really do. For example, integrate sine of t squared. Mathematica, what's the answer? Oh, Fresnel S. What's going on there? The reason it says Fresnel S is because there's no ordinary function that you're used to that is the answer. And that can actually be proved. You have to create a new function and say that's the answer. Somebody named Fresnel created this function and got it named after him. Fresnel S, that maybe S is because of the sign. If I change the sign to cosine, is it Fresnel C? I think so. Fresnel C. They're related to sine and cosine. They're non-elementary functions. So you could make up your very own integral function using an integral and give it your own name. Maybe you can even patent it. I think you can. I think you can patent functions that nobody's ever named before. Of course, you'd have to pay money to patent it, and probably nobody would care. So that's probably not worth it. Okay. But you get the idea. It's a method to solve the differential equation that goes beyond just guessing when guessing seems too hard. We don't have really any other methods so far other than guessing and separation of variables. Here for exam 1. Will we for exam 2? Yeah, there are more methods coming. The main 2 other methods that come in chapter 1 are something called integrating factors and another one that is more guessing. Better guessing, you might call it. Better educated guessing in harder situations. And then in chapter 3, especially in the book, we're going to be dealing with systems of linear equations, linear differential equations, not just algebra equations. And we'll be solving those using matrices and vectors. That's where the linear algebra comes in to play in the biggest way in the class. Something called eigenvalues and eigenvectors are very prominent there in chapter 3. That comes on exam 3, I think. About 6 weeks from now. So do we give up after that point in chapter 1? No, what's the next topic? Remember without looking? SLO. Yeah, slope fields. What are slope fields about? Slope fields are a way to use technology, essentially, to sketch solutions without finding formulas for them. I mean, you could do it without technology, but that would be a real big pain. But the idea is you've got a first order differential equation. First order means there's just a first derivative. There are second order equations, as we will see fairly soon, that involve second derivatives. Actually, with free fall, if you write the differential equation in terms of the velocity, that's a first order equation. But if you write it in terms of the height, that's actually a second order equation. So it's a pretty simple second order differential equation. The right-hand side function in general depends on both t and y. If I give you a slope field, you should be able to sketch solutions. Would I have you sketch a slope field from scratch? Probably not in the in-class portion. Too time consuming. Maybe a couple of line segments. I wouldn't have you draw more than a couple. But the idea is you've got a ty plane. Pretend this right-hand side function here. By the way, the right-hand side functions they're not solutions, right? They just define the differential equation. That's all they do. And they define the slope field. Solutions are not the f's, they're the phis. You solve for y as a function of t, sometimes call it phi of t. Solutions have to follow the slope field. At every single point in the plane, take a given point, what are its coordinates, ty, make a little line segment centered at that point, whose slope, this says slope if it's not big enough for you there, is f of ty. Solutions have to follow the slope field, so if a solution passes through that point, this little line segment's got to be tangent to the solution. Say it like that. I drew that concave down, I could have drawn the concave up. I'm not saying anything about this general situation. It could be either. And it's got to do that for all points. So the other points it passes through, if you look at their line segments from the slope field, they have to be tangent as well. And that can help you sketch solutions. That's the purpose. And if you can sketch solutions, that means you can describe the real life behavior of whatever it's modeling, in the long run at least, without finding formulas. Just looking at graphs. That's a useful thing sometimes. Oftentimes, actually. Because oftentimes differential equations are just too hard to solve explicitly. You have to rely on slope fields or Euler's method or something better than Euler's method. There are plenty of numerical methods better than Euler's method. If the right-hand side function just depends on t, it's an f of t, that is technically the simplest kind of differential equation, though we're more interested in situations where the right-hand side does depend on the y as well. You're looking for a function whose derivative with respect to t is always f of t. You're looking for an antiderivative of f of t. In calculus, you always call it capital F. Here we can call it phi, or capital F. And you know from calculus that solutions, integrals like this, always have plus c's when you integrate them, and that means solutions are vertical translations of each other. And for the slope field, it means the slope field is constant along vertical lines. On any vertical line, all the slope marks are going to have the same slope. Different vertical lines, they might have a different slope. And there's a geometric reason all the solutions are vertical translations of each other. On the other hand, for an autonomous equation, which we're really more interested in, where the right-hand side depends just on y, this is called autonomous equation. You know, the generic meaning of the word autonomous means independent. Here we're saying it's autonomous because it's independent of time. It's not changing over time, is the reason for the terminology. There, the slope field marks are constant along horizontal lines. And solutions are going to be horizontal translations of each other. And you often have equilibrium solutions, maybe here and here. Equilibrium solutions, which are constant functions that solve the differential equation. That says equilibrium solutions if you can't quite read it.
What were the ones that
These here, you mean? For this kind of differential equation, I call it a pure antiderivative problem. You're just looking for an antiderivative of little f. And solutions are vertical translations of each other. The book doesn't give this a name. Pure antiderivative problem is my name. Autonomous, that's in the book. Solutions are horizontal translations of each other, like this. We're more interested in thinking about autonomous equations because they're more interesting. That's why. Do they come up in more applications? Yeah, at least in this class. Equilibrium solutions, again, are constant functions that solve the differential equation. Again, in both of these pictures, t is horizontal, y is vertical. But another big theme is you should be able to, for autonomous equations, graph the right-hand side function and use that to draw the slope field, roughly speaking. And then when you make such a graph, y becomes the horizontal axis. And you could say dy dt is the vertical axis, dy dt equals f of y. And for a situation like this, maybe the graph looks like this. In fact, this is the kind of thing you see for a logistic model. Logistic model is something you should know. If you look at last year's take-home exam, I put a logistic model problem on it. It's a population model, more complicated than exponential growth. This is not a solution of the differential equation. All it is a graph of the right-hand side function, which helps you draw the slope field. That's its purpose. Y is horizontal here and vertical there. That's a good idea to have it horizontal here because you're graphing f of y. It's a good idea to have y vertical here because y is going to be a function of t. You got to be able to go back and forth between these pictures. You're going to have equilibrium solutions at the values of y where this right-hand side function is 0, like y equals 0, and say this is y equals 5 there. If that's y equals 5 there, and this is the slope field for this differential equation, this is going to be y equals 5 there, where you have an equilibrium solution where this function equals 0. Can I clarify anything there? I know I'm going kind of fast, that I'm assuming, you've thought about this some and you've worked on some problems, you've done the reading, you've watched the lectures. If this were really f of y, I'd also could continue the slope field. When y is bigger than 5 or less than 0, you see the outputs here are negative, so the slope field must have negative slopes. But again, be constant along horizontal lines. More solutions, if you drew them in here, would look like this and like this. There's always still infinitely many solutions of the general differential equation, though if you have an initial condition, then there's going to be just one, typically. Except there's that existence and uniqueness section as well. Okay, that's qualitative stuff. That's slope field, section 1.3, and I hinted at existence and uniqueness. We also have Euler's method. We haven't taken the time to do Euler's method example in class, but certainly simple examples could show up on the test. I also do want you to know the Mathematica method for implementing Euler's method using nest list that came up on homework. A little weird, but it works, and it's probably the best way to do it on Mathematica. So there's Euler's method. It's a numerical approximation method, approximating solutions to differential equations. It involves a difference equation. I'm not going to write it down because we got to get to some linear algebra here too, and we only have 15 minutes left. Existence and uniqueness is some theory that comes up in section 1.5, uniqueness. And the most important things to realize is that if the right-hand side function is nice, okay, let's write the initial condition more generically. Y of t0 equals y0. If this f of ty is nice near the point with coordinates t0, y0, t0 is usually 0. What does nice mean? Continuous. As an example of what it means for the right-hand side function to be nice. Solutions will definitely exist. A solution to this initial value problem will definitely exist. For example, when you're using Euler's method, you're not approximating something that doesn't exist. That's good to know. With uniqueness, seeking a unique solution of the initial value problem, you do need an extra hypothesis. Not only should this function be continuous near the point, but its partial derivative with respect to y should be continuous. That comes up as well. The derivative of f with respect to y. Still a function of t and y. Is a net, assuming that's continuous, excuse me, near the point, is one hypothesis that you can make that will guarantee not only will the solution through that point exist, but it will also be unique. No other functions will solve it. In the reading and in the lecture, there is at least one, maybe two examples where uniqueness fails because this partial derivative fails to be continuous near the point. The most important consequence of uniqueness when it applies, when this function and this function are continuous, is that distinct solutions can't touch each other. That's the most important practical consequence. It is a useful consequence because sometimes you might know certain solutions, but not other solutions. And if you know two solutions are, one's higher than the other, and you got an initial condition between them, then the unique solution of that initial value problem has got to stay between them for all time because the graphs can't touch. And that's useful sometimes. Then there's the implicit solutions, like we did an example of here at the beginning of class. That's not in our textbook, but it's something that I want you to learn about from the lectures. I also talk about in conjunction with slope fields as well, using Mathematica to make contour plots, contour maps that help you draw slope fields. Essentially, you're drawing curves in the plane where this function is constant. Simplest example is when that's a linear function of t and y. We did an example of this in class about a week ago. We drew some lines on the board, and we drew, those were not, it was in the slope field, but those lines were not the slope field of the marks themselves. They helped us draw the slope field to figure out where the slope was 0, where it was 1, where it was 2, about a week ago. That helps you draw the slope field. In the case, especially where the right-hand side depends on both t and y, which is not this case, and it's also not that case. This is big, broad overview of stuff. Okay. Let's finish talking about linear algebra now. Linear algebra. These subjects are not really coming together at the moment. They come together in a real big way in October. What have we talked about? Linear algebra, visual linear algebra online, and also the lectures. The starting focus, initial focus was fairly simple, just coordinate systems, including the basic idea of a skewed coordinate system, including skewed coordinates. And you've got an XY coordinate system describing points in the plane, but well, your axes don't have to be horizontal and vertical, and they actually don't have to be at 90-degree angles from each other. You could add a U-axis and a V-axis like this, and that defines slanted graph paper that could also be used to identify points in the plane and make graphs and that kind of thing. Seems like a really weird idea, like why would you ever do such a thing? But we'll see is in chapter 3, it's actually very useful to give yourself the flexibility to do that. Because some problems are more easily solved in skewed coordinates than in ordinary coordinates. Then we talked about vectors. Certainly the basics of graphing them and adding them and subtracting them and multiplying them by scalars. Vector algebra. And geometric interpretation. Related to that, we also got into dot products. Both how to compute them if you've got the components of the vector and the geometric meaning. V dot W is the length of V times the length of W times the cosine of the angle between them. It can help you figure out the angle between them if you need to. Related to that is also projection vectors. In one of the lectures, I emphasized application of projection vectors to a physics problem. mass on an inclined plane. Your force is not parallel to that plane. It's in some other direction. To find the work done, you got to figure out the projection vector along the plane, and well, that's one way to do it. Or you can actually just dot the force with the displacement vector. And we've been talking about projection vectors recently. The formula for the projection of V along the line through W, again, is V dot W divided by W dot W times W. And realize this is a vector. This thing in parentheses is a scalar, but it's times a vector, so the whole thing is a vector. Projection vectors are really useful, not just for physics. Another example of situation where projection vectors are useful is statistics, actually. They actually end up being useful in statistics. And this generalizes as we go through the course as well. In class on Wednesday, you dealt with projection vectors to try to figure out a linear transformation that did a reflection. If you look at last year's take-home exam, I gave them a problem like that. Not guaranteeing it'll be on your test, but it could be. What else comes up? Systems of linear equations. If it's two equations and two unknowns, that's definitely the easiest kind of system to solve. Real quick summary, if one equation is a constant multiple of the other, there's going to be infinitely many solutions because they're both going to represent the same line. If they're not multiples of each other, then they're different lines, and there's just going to be a single solution, one point of intersection. But then we do more recently starting to get into higher dimensional systems. For example, 3 equations and 3 unknowns. And you should make sure you can do row reduction to solve those. Well, I'd let you use your calculator, possibly. RREF, reduced row echelon form on the calculator. But you should be able to do it by hand if I ask you to. The row reduction steps to reduced row echelon form. It's simplest in the 2x2 or 3x3 case. If that's not sounding familiar to you, you've got some studying to do there. Linear transformations come up as well. Section 1.4, it's in 2-dimensional, R2 to itself. Examples included reflections, rotations, shears. There are more complicated examples too, but those basic examples. And what you should be like reading right now and or over the weekend is higher dimensional ones, like from 3-dimensional space to itself, with a focus on things called kernels and images. Maybe you haven't quite gotten to that subject yet. What are kernels and images? If you got a linear transformation, T, which is a function, say from 3-dimensional space to itself, and it's a linear transformation, the kernel of T is defined to be all the vectors, all the points, if you prefer, in the domain that get mapped to the 0 vector in the codomain. All the vectors, column X in the domain, both the domain and codomain are 3-dimensional space in this example, but you think of the domain as going there with the property that T of X equals the 0 vector, where that's the 0 vector in the codomain, which also happens to be 3-dimensional space. All the vectors that get mapped to the 0 vector. that ends up being equivalent to the solution set of what's called a homogeneous system of linear equations, where the right-hand side numbers are all zero. And it's fundamental to understanding solutions in situations where the right-hand sides are not all zero, it turns out. So a very important concept there. And the image of T is the set of all outputs of the function. You could call this the range of T as well. I prefer the word image. What are all the outputs of this function? All the outputs T of X, where that X you think of as being in the domain, as X ranges, over the domain. T of X itself, the output is in the codomain. Both the domain and codomain happen to be three-dimensional space in this example that I'm imagining here. What are all the outputs? Last thing to mention, related to this, is the idea of a one-to-one function and an onto function, which, technically speaking, are ideas you should have learned about back in high school. Maybe you forgot. One-to-one functions, distinct inputs get mapped to distinct outputs. That's not the same as what a function is. Excuse me. Yeah. For a function, every input gets mapped to one output. For a one-to-one function, every output has one input that gets mapped to it. So distinct inputs get mapped to distinct outputs, not the same. X squared is not a one-to-one function. 2 squared equals 4, but negative 2 squared also equals 4. Linear transformations are going to be one-to-one if and only if their kernels are trivial, just the zero vector. The only thing that gets mapped to zero is zero. Onto means the image is the entire codomain. Every element of the codomain is a possible output of the function. So yeah, I know I went very quick over a lot of ideas that are pretty subtle sometimes. Okay, keep working. Have a good weekend.